Right, kids, we've got a problem here where we want to find the slope of the tangent line and write an equation of a tangent line to this problem. And the tricky thing with this problem is because we've got x and y mixed together, here you can see it right here in cosine of y, we're going to have to use what's called implicit differentiation, which means that now when you take the derivative of y, you're going to have to use the chain rule and multiply by dy dx. So in order to find a tangent line, I need to take a derivative and define that slope. So here's my derivative. By the way, product rule right here, 3x squared is one thing, y is another. So the first times the derivative of the second plus the derivative of the first times the second minus pi times the derivative of the cosine, and then the derivative inside the cosine now is dy dx. Don't forget to take derivative on the other side of the equal sign. The derivative of 4 pi is 0. Now, in order to find the slope of a tangent line, we have to figure out what the derivative is. What is that? And that means that we've got to isolate and get all alone the dy dx's. So we're going to actually treat dy dx as our variable of old in algebra. And we're going to get everything that doesn't have dy dx in it and move it to the right, and then we're going to factor dy dx out. So how's that look? Well, here's what we're going to do. We're going to subtract 6xy from both sides. And when we get done doing that, see if I've got the right color here. When we get done doing that, we're going to have 3x squared dy dx plus sine y dy dx equals negative 6xy. And then notice now I've got these dy dx's right here. So what we're going to do is we're just going to factor out the dy dx. So this guy right here and this guy right here, they can come out into the front, and that gives me dy dx. And then on the inside still, 3x squared plus sine y. And to finish, then we would just divide both sides by 3x squared plus sine y. That's all we have to do. So dy dx, the derivative then, is equal to negative 6xy over 3x squared plus sine y. Okay? And what does this mean? This means that I can now find the slope of a tangent line at any point on this equation, 3x squared y minus pi cosine y equals 4 pi. I can find anywhere on this equation now a slope. And how do I do that? Well, I substitute in x, my x coordinate in for x, and my y coordinate in for y. So I'm going to get negative 6 times 1 times pi over 3 times 1 squared plus sine of pi. And when you simplify this guy down, you end up on the top with negative 6 pi, and you end up on the bottom with sine of pi is 0, so that's just going to be a 3. So the slope on this particular problem is negative 2 pi. And if I need to find the equation of the tangent line, I've got x and y, and now I have slope. So using my point slope form of an equation, y minus y1 equals m times x minus x1, I've got all those now. So y minus the y coordinate equals the slope times x minus the x coordinate. And if you're just convinced that you have to have an equation that says y equals, then go ahead and add pi to both sides. But you really don't need to do anything after that because you may or may not make a mistake, and this is the equation of a line. Like I know exactly how to graph this line. Okay, so there you go, implicit differentiation and tangent lines. All right, in this problem we're going to look at the derivative of the arc cosine, and this is a pattern sort of derivative. It's really different from the regular trig functions. It's a little bit tricky. So what we're going to do is we're going to use the pattern for arc cosine, which I've given to you here as well in the kind of the purpley ink. The only thing that I would add to this is that we want to make sure that we multiply by du dx on this edge, okay? Because we've got more going on in our problem than just x. We've got this. Whoa, how to handle that? Well, here's what we're going to do. We're going to let y equal negative cosine, arc cosine, and we're going to look at this as x to the negative third power. That's the same exact thing as 1 over x cubed. And what I'm going to do is I'm going to say u equals x to the negative third, and we have to take derivative of that. This is going to be the chain rule part. So it looks this way. Now, that's a good derivative right there. Depending on how our problem works out, we may also want to look at it this way, and those are equal things, okay? I don't know. I don't know. We may want this guy. We may want this guy. Not sure. So back over here to this problem, y equals negative cosine, and I'm going to just rewrite this. Y equals negative arc cosine of u. Now this is a lot easier to work with. I can follow this pattern right here now. So negative y dy dx equals negative, I got to bring that negative down, and then negative 1 over the square root of 1 minus u squared times the derivative of u, du dx. And we're almost done. The very last thing to do is just re-substitute in those values. So this guy right here, this u, goes in here for this u. All right? And this guy right here goes into this guy right there. And once we make those substitutions, we're probably going to be okay. I don't know that we'll have to do a whole lot else. We'll just have to wait and see. But I don't anticipate a lot more work coming our way. Well, negative times negative is positive, so that takes care of that. 1 over the square root of 1 minus, and I don't care for my personal experience, teaching style, whatever. I don't care if you write it this way or this way for your u. I'm not super picky. Check with your teacher and see what your teacher prefers. For my kids, this is acceptable right here, and then times negative 3 over x to the fourth. Okay, now take one more step to simplify all our loose ends. So that's going to end up being, let me just double check, yep, negative 3 on the top here over, and then on the bottom, x to the fourth times the square root of 1 minus x to the negative sixth. Now, you can treat this x to the negative sixth as a fraction. You could get a common denominator with the 1. You could do all this fancy stuff. I'm satisfied with this answer. If you want to work on simplifying out the radical so that you've got no negative exponents in there, I'm not going to take all those steps and show you right now, but I will tell you that the answer should be something like this, negative 3 over x times x to the sixth minus 1. Both of these answers are good answers. This is with some simplification. This one's fine. Just check with your teacher and see which one they prefer. This problem takes a look at finding the derivative of e, and this has got to be one of the most favorite derivatives of all calculus students because it is so simple. The pattern that we're going to follow for e, if we look at d dx of e to the u, this is what we're looking at. This is going to be e to the u du dx. And so that's all there is to it. Ignore the children in the background. I have no idea what they're doing. The house is not on fire yet. So what we're going to do then is we're just going to let this guy up here become an u. So u equals negative 4x. And because of chain rule, every time we make a u substitution, we have to find the derivative of that u. So that takes care of this part. So what we're actually going to work with then is f of x equals 8e to the u. Well, the derivative of that, look at here, is just going to be 8e to the u times du dx. Well, we know what du dx is. It's 4. So what I'm going to do is I'm going to take this 4, and he's just going to go right in here for this guy, and I'm going to just put my negative 4x back in for u. And what happens is I end up with 8e to the negative 4x times negative 4. Now, there's a couple different ways that you could write this. 8 and 4 can be multiplied together because they're just constants, okay? So I've got negative 32 e to the negative 4x. Now this is a good answer. It's a correct answer. There's nothing on there that would indicate that you haven't done what you're supposed to do. But some teachers don't like negative exponents, even though we started with one. So what they would say is to move that to the bottom, so you have this situation happen. Both of these answers are correct. They're both good. They're both derivatives of 8e to the negative 4x. So there you go. Okay, different derivative this time. Now looking at a logarithm, but not a natural log. This is anytime you have a logarithm without anything there that you can visibly see, we're going to treat this as a 10. So this is a logarithm base 10. And the derivative of a logarithm, if we look at that pattern, d dx of log base b of u is equal to 1 over u natural log of b times du dx. All right. So on this one, I'm going to let my u be this 8x minus 4 guy. So what I'm actually going to be working with is f of x equals log base 10, which I'm not going to write, but there it is, you see it, of u. And what is u? U is 8x minus 4. And anytime we do chain rule, we've got to take derivative of u. So du dx is equal to 8. Now, back over here for my derivative. F prime of x then is going to be this pattern right here. 1 over u times the natural log of 10 times du dx. All right, and so to just finish this guy off, we would just resubstitute in those values that we said that were going to be u and du dx. So 1 over u, which is 8x minus 4, put it in parentheses, times the natural log of 10 times 8 over 1. Wow, that's a really ugly 8. I'm so sorry. So to clean it up, you can have 8 over 8x minus 4 times the natural log of 10. Or you might notice that I have a 4, a 4, and a 4. I've got all those guys going together. So I could, if I wanted to, cancel. I could factor a 4 out of this, which would make it 2x minus 1. So I could have 2 over 2x minus 1 times the natural log of 10. Both of those answers work. I don't have a problem with either one, but that's how you take a derivative of not the natural log, but another log of different bases. All right, with this particular problem, what we want to do is we want to try and figure out exactly what the original function is. They tell us that f prime of x equals 6 cosine 6x. And I think, let's see here, the exact instruction is, because I didn't copy that part, find all possible functions with the given derivative. So in other words, what we're trying to do is go backwards from our derivative to what our parent function might have been. The derivative of what, okay, gives me this guy. So let's just think about this real quick. The derivative of the cosine, derivative of what is cosine? And the answer to that has to be the sine of x. So this is going to be sine of x. Now, remember what we've learned about trig stuff. If there's something inside the trig function, it has to be there with the original function. So we're going to start here. And of course, the derivative of a constant is 0, so we have to add a plus c. Now that's a hard one to remember, the plus c, but you've got to add it every single time. Don't forget. All right. And so here's where we can start from now. Let's just ask ourselves some questions. What do I need to multiply the sine of 6x by so that when I get finished finding the derivative, I get to 6 cosine 6x? So let's just run over here real quick. If I start with the sine of 6x and I take plus a constant and I take a derivative, the derivative of sine 6x is cosine 6x times the derivative inside the trig function, which is 6, plus the derivative of the cosine, which is 0. And so when I check this out to see what I'm missing, it looks like nothing. It looks like nothing. So I got back to where I started from by taking the derivative of my original function. So there you go. All the possible functions that can be created by taking the derivative, which gives us a derivative of 6 cosine 6x. All those possible functions start from sine of 6x plus c plus a constant. All right, so starting with question 16 here, what we're going to talk about is trying to find where this function has increasing and decreasing behavior, or maximums and minimums, and also where this function has concavity up or down. And to find those things, we need to know the first and second derivatives. So the first derivative is going to tell us where we increase or decrease. The second derivative is going to tell us where we're concave up or down, or where we have points of inflection. Okay, so a lot going on in this problem, and what we're going to do is just kind of break it up into two spots. We're going to break it up into first derivative. So the first derivative is going to be 3x squared plus 8. The second derivative is going to be 6x. So here's our two derivatives right here, and what we want to do is set each one of these equal to 0 and solve it out, because when we set it equal to 0, that gets us what's called a critical point. And it's a critical point because things happen at critical points. That's why they're called critical. All right, so here we go. 3x squared equals negative 8. Divide both sides by 3. And guess what? X squared equals negative 8. If I take the square root of both sides, there's no place I can do that. Okay, so this is always going to be positive. So when I look at a number line, I don't have any 0 values at all for this particular problem. And so what that means is, since I have no 0 values, anything that I square is going to be positive. So I get a big old plus on this guy, which means that my graph is always doing this. All right. Now, if I had been able to work it out, like if this said x squared equals positive 8/3 or something like that, and then I take a square root, that's a little bit different. But I can't do this one. And so when I just put values of x, remember values of x right here into 3x squared plus 8. No matter what value of x I pick, I will always get a positive number out of that, always. If I put in a negative 2 right into here, I'm going to get a positive number out. If I put in 400 from over here, I'm going to get a positive number out. And remember, when we're looking at a sign chart, we just need to know whether a number is going to be positive or negative when we apply it to that particular derivative. Okay, so for this particular guy, where are we increasing? We are increasing from negative infinity to positive infinity. Okay, so this graph increases from negative infinity to positive infinity, and not only that, there's not really a max or min here, because we did not get a specific 0 for this particular problem. Okay, let's check out concavity. So we've got 6x equals 0. I'm going to divide both sides by 6, so x equals 0. So on that number line, I do have a number of 0, and I check it with 6x. Okay, and so when I pick a number less than 0, like say negative 2, I put a negative 2 in here, I get a negative number out. When I pick a positive number, like say positive 2, and put it in here, I get a positive number out. And all we're doing is we're putting negative 2 in for x, and we're putting 2 in for x. And what kind of number do we get, positive or negative? The result then is that I am concave down from right here. I'm concave up right here, okay? So what does that tell me? Well, let's just record this real quick. So I'm going to write down here that we are down from negative infinity to 0, and we are up from 0 to positive infinity. Now, since my concavity changed at 0 from down to up, since my concavity changed at 0, we have a point of inflection at 0. And exactly what point are we interested in? We're interested in our original function when the x-coordinate is 0. The original function when the x-coordinate is 0. That's what we're interested in. So come back up here. We're going to do f of 0, which is going to be 0 cubed plus 8 times 0 plus 5. What do you get? You get a 5. So there you go. That is the point of inflection for this problem. So where are we increasing? From negative infinity to positive infinity. Where are we decreasing? We don't. Where are we concave down? From negative infinity to 0. Where are we concave up? From 0 to infinity. And what point of inflection do we have? In other words, where is that concavity change? It changes at the point 0, 5.